Okay, so I'm Bryan Chastain. A little bit of background. I am a faculty member at in the Geospatial Information Science program at UT Dallas. A little bit of background on me. Our faculty is really well versed in spatial analysis and spatial statistics, but when they've developed all sorts of great tools and techniques for this over the years, world leaders and that kind of stuff. But they're all very focused on R and SAS and other programs. Nobody else really, besides me, really uses Python. And they've developed some really cool things, but I'm trying to get them to use more Python and try to use some of the PySol techniques from Arizona State and things like that. So I'm trying to incorporate some of their ideas into some of the Python using NumPy and some other software. It's kind of hard to see on the screen over there, but there's a URL for the slides and the code. It would be a footer on all of those slides as well. So starting out, a little bit of background on spatial analysis, and some of this goes to what Wei was talking about earlier, but most of your linear models that you're used to using in statistics, your OLS and things like that, they have a common set of assumptions, namely ID, so things need to be independent and identically distributed. And that's not too big of a problem when you're working with traditional statistics. You can kind of take things into consideration, look at the variation between different variables and things like that. But when you're working with spatial statistics, you have this phenomenon called spatial autocorrelation, where things are more similar nearby than they are farther away. So a classic example would be temperature. I can tell you the temperature across the street if I know the temperature here, because it's going to be very similar to one another. So because of that, you have to think about model misspecification errors, because things aren't necessarily independent anymore if your residuals have some spatial autocorrelation here. So here's the residual map of a spatial regression, and you can see that there's clustering kind of all throughout the data set there. So if you have that spatial autocorrelation in residuals, you really have a model misspecification error, and you can run into a lot of different problems when you're doing your modeling. So what can we do about that? So how do we control for our spatial autocorrelation in our models? Well, there's a lot of different techniques. One of the most popular is a technique called geographically weighted regression. And it's been one that's been kind of widely implemented in different software, ArcGIS and R and other different types of platforms have used it. And it's really popular because it's really simple to use, but I think gets a little bit overused because it's really more designed as an exploratory tool, kind of as a simple way of controlling for spatial autocorrelation when I explore my data. It's been shown in some articles, not really a great model for looking at inferring parameters, things like that for more formal models. So a few other different techniques have been developed. I won't get into all these different ones, but all sorts of different backgrounds from parametric and non-parametric and linear and non-linear and frequentist and non-frequentist, all different types of ways of trying to handle this problem of we have spatial autocorrelation, how do we control for it so we're not having this model misspecification error. One of the, I don't want to say newest, but one that's been shown to have a lot of the most promise by some of my colleagues at UTD has been this eigenvector spatial filtering. And so there's been some papers showing that it's an unbiased, efficient, consistent estimator for linear regression, also for different variations for nonlinear as well. And it has been shown to outperform a lot of those other techniques that I just showed in the last two slides. So how does this ESF work, this eigenvector spatial autocorrelation, that's the spatial filtering? So basically how it works in the most abstract sense, it splits the data into spatial and non-spatial components, and then you use them in an OLS framework, for example. First, as in Wei's presentation, there's a spatial weights matrix. In the most simple form, it can just be an adjacency matrix. So this is connected to this, so that gets a 1. This is adjacent to that, so that gets a 1. And it could be depending on, do they share a non-zero border or not? And there's all different types of forms. You can row standardize that matrix. You can double standardize it. And all sorts of different variants on that. But it's the basic idea of this spatial weights or links matrix, how things are connected to one another. So you take that, And then you perform basically get this projection matrix by multiplying it by these vectors here. And it causes, through this operation, it causes the first eigenvector of that matrix to be replaced with a constant vector and 0 eigenvalues. And so that means that because of that, the eigenvectors of your result here represent all the distinct and uncorrelated spatial autocorrelation map patterns. So when you come up with these eigenvectors of this matrix, all the eigenvectors are distinct map patterns that represent different levels of spatial autocorrelation, which you can then try to select from those eigenvectors which ones might be most useful for your model and account for that in your model. So here's some example. This is from one of my colleagues' papers looking at a Georgia data set. But you can see that these are just a sample of 9 different eigenvectors that have been selected. You can see they have different clustering patterns, and so depending on your particular data set, one or more of these may be more relevant to your particular variables in terms of how things are clustered in yours. So it's all a matter of selecting which one of these eigenvectors would account for most of the spatial autocorrelation in your data. So there's several different forms of this eigenvector spatial filtering, but I was particularly interested in looking at the semi-parametric form. And there's, like I mentioned, there's other ones for nonlinear, Poisson logistic, other ones. But and the linear regression form of eigenvector spatial filtering has some nice properties that the eigenvectors that you come up with in that last calculation have a nice property of being mutually orthogonal. So that means that if I do a stepwise either forward or backward selection, I'm going to get identical sets of eigenvectors that I'm selecting from all my candidate eigenvectors. And so you keep adding eigenvectors to your candidates list until the spatial autocorrelation left falls below a threshold. So once it's non-significant or close to 0, you can kind of set that threshold at whatever you think is most appropriate, and then you've got your final set of eigenvectors for use in your parametric model. Like I mentioned, my colleagues are really fond of using SAS and R. In particular, most recent development has been a function in the SPDEP library package in R for doing semi-parametric eigenvector spatial filtering. But there hasn't been any for Python or in GIS, such as ArcGIS or QGIS. So that's what I was particularly interested in looking at. So I took a look at that spatial filtering function from our SPDEP library and tried to and brought that into NumPy using NumPy and PySal to do it. And so I'm going to go over the function. You can see the code in the bottom to a link to see the full code. But this is kind of a brief description of what the function looks like if you were to call it. And so I'll go through some of these different variables here. So some of the parameters, you of course have to give it a dependent variable. So what am I trying to model? Then you either can work with a set of, this semi-parametric either works with a spatial error model, or you can also work with lag variables. So you can include lag variables or not. So you have an option of using just your independent variables or have them be lagged or have some combination between the two. So that's where the different your independent variables can either be in the independent set or they can be in the spatial lag set. Then the data set is just the DBF file from a shape file that you can get from. You could also convert that from using some other libraries. Then there is the neighbor list, and this uses the GAL format, which can be generated using PySal or Geota, which is just an encoding to set up that link matrix, what's connected to what. There's some functions in PySal and Geota to just connect to generate this GAL file for you really easily, and the different styles you want to work with. Then there's the style, which is just telling what style of matrix, spatial weights matrix am I going to do? Am I doing just standard binary, or am I going to do some of those other variants, including row standardized or variant stabilizing, things like that. Then there's some other more optional parameters. You can work with a zero policy to say, where do I want to stop when I'm going with my, sorry, that's the tolerance. You know, how do I, the tolerance is where am I going to stop for my convergence and my spatial filtering. The zero policy is, you can set it be true or false to stop with an error or not based off empty neighbor sets, just looking at how you have your weights list set up. There's the zero value, which tells you how am I going to allow for the minimum values of eigenvector or eigenvalues for your eigenvectors. There's exact EV, which is an alternate formulation. Just these are some little tweaks and parameters you can work with, but setting that looks at the Moran's eye, actually recalculates it instead of using the previous iteration. There's symmetric, which forces your spatial matrix to be symmetric. There's alpha, which is another variation to check against the tolerance, just a different way of checking the tolerance for convergence. Then there's the alternative for your alternative hypothesis, or are you doing a one-tailed or two-tailed test for your hypothesis? And then verbose just prints out more logs, gives you some more detailed logs along the way. Then in terms of output, two main things are output. One is just printed out on the display, which is just a table of your results, so the stepwise selection of your eigenvectors. It tells you, okay, each step, which eigenvector was selected, what was the Moran's eye, which is a measure of their global spatial autocorrelation after that eigenvector was selected, and it goes through until you've selected all your eigenvectors, so you can see what the Moran's eye and the p-value from the Moran's eye is there. Then in addition to that output table, there's also a matrix that's output as well, and that matrix is a matrix of all of these selected eigenvectors. So then you can join that that matrix of eigenvectors back to your original data for use in your OLS or other types of regression models. So here is an example, and so this one it requires PySal, and NumPy and SciPy, of course. And this is just using an example data set from the PySal library. And so I'm getting my dependent variable, which is crime, and independent variables, which I think in this case were income and home values. And then I'm saying set up, and there's a weights matrix, that Columbus connection. Then I said I'm going to use row standardized weights. And then I pass it, I call my spatial filtering. I didn't use a lot of those optional parameters. In this case, I just said I'm going to use my dependent variables, my independent variables, told it where the data set is, what my gal file is, and which format I'm using for the spatial weight matrix. And so as a result, it prints out the out table here, which shows I had 5 steps through that iteration. I see that I selected eigenvector number 5, number 3, number 1, number 10, and number 14, and it shows you minimize the Moran's eye, showing the Moran's eye decreasing as you've gone, and the p-value associated with that Moran's eye. So now there's no significant levels of spatial autocorrelation left. And so then, as a result, I didn't include this, and the next step would be you would take those 5 eigenvectors, 5, 3, 1, 10, 14, and then use that back into your original regression, be it OLS or whatever type of regression you're doing, and then that would be your component, component of that regression to control for your spatial autocorrelation. This is just an example. I showed that one of George earlier. This is just another eigenvector. This is eigenvector number 1 from one of those data sets, and showing the clustering from that particular example. So we at UTD, we use ArcGIS a lot. I know it's not cool to talk about proprietary software at an open source conference, but I do use this a lot. And so there's 2 components to this. There's the tool, which I just showed you, the code to call that function to do that spatial filtering, but then there's also a separate front end, in this case for ArcGIS. And so includes the option to basically, it has all those same, it's just a GUI interface to the same parameters that I just showed you in the Python function, but you've also have a couple other options, like I can have my output eigenvector table automatically joined to my shape files so I can quickly and easily visualize my eigenvectors if I want to do that. There's a video on here, which I'm not going to make you sit through the whole thing, but it's just showing you basically what the interface looks like. So here I'm selecting my input file. I'm selecting I'm selecting I think this is a bladder cancer example, looking at bladder cancer compared to population density and lung cancer. And so I'm using that as my dependent variable and independent variable. I'm selecting my GAL file, selecting the type of the style I'm using for that GAL file, and then selecting my outputs. In this case, I'm outputting to a layer file to join the matrix back to the eigenvector matrix back to my original data set. Part of the reason I was interested in doing this was not only to bring some of those interesting tools from R and SAS into Python, just so I could have access to it. But you could do that without having to recode it. Like there's RPy and things like that to call R from Python. But I had a suspicion that it may be improved performance running it in Python versus running it in R. So I did a little test, and I compared. I thought the most fair comparison would be I did the Anaconda Python versus the Revolution R Open, both of which uses the Intel MKL libraries. So, but in all three of my tests here, the NumPy version, the part version I wrote, seemed to have increased improvements over the R version. But in all cases, once you get to not even that large a data set, this is just on my desktop computer, not that super powerful, but once you get over 1,200, 2,000, things start really slowing down. So you might either write it more efficiently. I probably didn't write it the most efficient way, or really increase your computing power to handle big data sets for this type of analysis. So other future things I'm going to work on. I wrote this in Python 2 just because in ArcGIS is all written in their libraries are in Python 2, but some of the newer stuff is getting in Python 3. And the new product of ArcGIS Pro is with Python 3 as well, so I'd like to rewrite this for Python 3. Also, like I mentioned, it's two pieces. It's the main function is in one module, and then I have the front end, really simple front end to the GUI for ArcGIS. So there's no reason why I couldn't write this for QGIS as well, other open source GIS software. That piece is really simple. It's just calling, attaching a GUI to the function to call it. So things like that. Other things I might want to look at are, this is just one particular type of eigenvector spatial filtering, the semi-parametric form, but there's other different forms as well, nonlinear and Poisson and logistics and things like that. We're going to try to incorporate those into Python as well. I want to thank my colleagues, Youngwon Chun, Michael Tiefsdorf, also Dan Griffith, kind of the innovators of these techniques and helping me out getting this into Python. Just a bit more information if you want to have any questions about UT Dallas or the GIS program or Python at UT Dallas, I'd be glad to talk to you. My email address and, of course, the slides and the code there is there as well.